Hello, good evening, everyone. So we will wait for 5 minutes and then we will start the lecture. We will wait for other people to join. So I hope everyone has gone through the week one lectures. Uh, So in this session, we will summarize whatever has been taught in week one, and also we will solve a few sample questions that will help you in solving your assignment. So I will start in another 1 minute. Uh, So, hello everyone. I am Akash Jyoti Pathak, and I am a PMRF TA for this course NMR Spectroscopy for Chemists and Biologists. I am a, PhD scholar here in IIT Bombay in the Department of Biosciences and Bioengineering, and I am working in NMR Spectroscopy lab. Since I'm working in an NMR Spectroscopy lab, and so I've taken up this course. So in the process, I can also learn, and in the process, I can also teach you whatever I know about this technique. So first, we will summarize whatever has been taught in week one. Uh, so, so, moving to the first point, as we know that in quantum, according to quantum mechanics, the nucleus, basically the nucleus has both mass and charge. Nucleus, what does the nucleus have? The nuclei have proton and neutron, and the neutron, we know that it does not carry any charge, it carries only mass, while the proton has mass and charge both. So the nucleus has a net positive charge. Due to this net positive charge, and by principle of quantum mechanics, the nucleus rotates about its own axis. Uh, so uh, It
Could
is
you go a
spinning.
bit slow, sir?
Am I audible and visible?
Yeah, you're audible and visible. Could you just go a bit slow, sir?
Okay, okay. Yeah, yeah. So the nuclei rotates about its own axis, and this is not in a physical sense, but this is a quantum mechanical concept. And since any particle which has a charge and is rotating will have its spin angular momentum, will have a spin angular momentum, which is denoted by the symbol P. So P is the spin angular momentum, and this is the expression of spin angular momentum, which is h by 2 pi root over I whole I plus 1. What is I over here? So I is the spin angular momentum, and the spin angular, sorry, I is called the spin quantum number, and this spin quantum number can have values 0, 1, half, 3 by 2. It can take any integer values. So, the now, I think you have gone through the lecture one. These topics have been discussed in quite amount of detail. I'm just giving a summary. So what happens that in NMR, we consider that the magnetic field is applied in along the z direction. Now, if we calculate the spin angular momentum along the z-axis, the spin angular momentum along the z-axis is quantized, and it is given by the expression mh by 2 pi. There will be spin angular momentum along the y-axis and x-axis also, but since the magnetic field is applied along the z-axis, so we will next discuss about the magnetic moment. The spin angular momentum along the z-axis is mh by 2 pi, and here m is called the magnetic quantum number or azimuthal quantum number, and it takes value from minus I to plus I. So if the spin quantum number is, for example, it is half, then m can take values minus half to plus half with increments of plus 1. So it will have minus half, take two values, minus half and plus half. And the nuclei takes a particular orientation, and these orientations, number of orientation that a nuclei will take is given by this formula 2i plus 1. Since the Now, what is nuclear magnetic moment? Since the nuclei is rotating about its axis and it has a charge, a dipole moment is because of a particular dipole moment. This dipole moment that is present is called the nuclear magnetic moment, and this nuclear magnetic moment is denoted by mu, and mu is proportional to the spin angular momentum. The spin mu is proportional to spin angular momentum, and when this proportionality is removed, we get a constant which is called the gyromagnetic ratio. And the gyromagnetic ratio is denoted by gamma. So here we get the expression mu equal to gamma h by 2 pi root over I into I plus 1. Now, coming to the magnetic moment. The magnetic moment is also, since the spin angular momentum is quantized along x-axis, the magnetic moment, so both the spin angular momentum and the magnetic moment are vector quantities. Since the magnetic moment, spin angular momentum so along the x-axis, the magnetic moment will be mu z, and it is equal to mh gamma by 2 pi. So what will be mu z? Mu z is basically mu z equal to gamma into pz. And the expression of pz, we know that it is mh by 2 pi. So from that, we get the expression mu z equal to mh gamma by 2 pi. Now, gyromagnetic ratio is a property of the nuclei, and it is given by the expression E by 2m, where m is the mass of the nuclei. So, the smaller the mass of the nuclei, the more will be the gyromagnetic ratio. And hence you have seen in the lectures that a table of the gyromagnetic ratio of the NMR active nuclei are given. So you will find that proton has the smallest mass and hence it has the highest gyromagnetic ratio. Now, what happens that in absence of any energy, the energy remains degenerate. Now, when radio frequency pulse is applied or energy is applied, the degeneracy is lost and the energy splits into two energy levels, which are known as the alpha state and the beta state. The alpha state is the energy state which has lower energy, while the beta state uh, has higher energy. So this is following the principle of Zeeman splitting effect, and whenever the nuclear magnetic moment interacts with a magnetic field, the degeneracy is lost, and it splits into two energy level. The energy of these energy levels is given by this expression E equal to minus mu z into H naught, where H naught is the magnetic field or the externally applied magnetic field. In an NMR instrument, we there is a conducting magnet which supplies this because of which this magnetic field H naught is produced, and the energy corresponding to this energy level is E equal to minus mu z into H naught. So now, what are the so what will happen is I have not written the expression. The alpha state has a azimuthal quantum number m equal to uh, plus half, and the beta state has a azimuthal quantum number m equal to minus half. So when you calculate the energy of these energy level alpha state and beta state, so the alpha state, it has m equal to plus half, so its energy will be minus half mh gamma gamma into h naught, and the energy level corresponding to the beta state will be plus half into h by 2 pi gamma h naught. So as you can see, that's this negative sign. Why is this negative sign present? This negative sign is there because the alpha state has a value of m equal to minus half. It will have a lower energy, while the beta state, it has a azimuthal quantum number m equal to plus half. It will have a sorry, beta has a m equal to minus half, so its energy will be higher than the that of the alpha state. So now what happens is the when this magnetic field is applied, the nuclear the nucleus spins about its own axis, and along with it, it also precesses about the externally applied magnetic field in the form of a cone. And the frequency with which the nuclei precesses around the magnetic field is given by gamma h naught, omega naught equal to gamma h naught. So why does this happen? What causes Larmor precision? Anyone? So, why does the nuclei precess around the magnetic when energy is applied? The nucleus starts precessing around the magnetic field in the form of a cone. And why does this happen? This happens because the nuclei has a dipole moment. Because of this dipole moment, it experiences a torque in presence of the magnetic field, and this torque causes the nuclei um, g- to rotate or rotate around the magnetic field in the form of a cone. And now, if you calculate the energy difference between the two nuclear spin states, that is E plus half and E minus half, or E alpha state and the E beta state, you can derive this expression, that is delta E is equal to gamma H B naught by 2 pi. Now, what is the main reason? what is the main reason that from which we get NMR signal? So the NMR signal is mainly obtained because of the population difference between the alpha state and the beta state. Since the alpha state has a lower energy compared to the beta state, the alpha state has more number of nuclei compared to the beta state. Now, because of this population difference, the NMR signal is obtained. Um and this the population difference between these two states is given by the Boltzmann statistics, and this is n beta by n alpha. N beta stands for the number of nuclei which are in the beta state, and L alpha stands for number of nuclei which are in the alpha state, and that is equal to e to the power minus delta E by kT. So what is delta E? Delta is the energy difference between the two states, and K is the Boltzmann constant, and T is the absolute temperature in Kelvin. So the ratio, the n beta by n alpha, the higher the ratio, the more will be the sensitivity of the detection of the signal increases, the greater the this ratio n beta by n alpha. And since E delta E, or the energy difference between the two energy levels, depends on magnetic field. So the more the magnetic field of the instrument, the greater will be the population difference. So for example, if you have an NMR spectrometer of 200 megahertz, and if you have an NMR spectrometer of 700 megahertz, then the difference in the two states will be more for a 750 megahertz NMR spectrometer, because delta E is directly proportional to the magnetic field. Now, what happens is the nuclei which are present in the alpha state and the beta state, they can transition they can transition between the two energy states, and the probability of the transition is proportional to the square of gyromagnetic ratio and the square of the magnetic field. So, mm, so yeah. So when we are basically what happens is when we are applying a radio frequency pulse, this radio frequency is an electromagnetic radiation, and the electromagnetic radiation, as we know that it has both a magnetic field component and a electric field component. So the magnetic field component of the radio frequency pulse is given by the expression H1 cos omega t, where H1 is known as the amplitude of the radio frequency pulse. So the transition probability is directly proportional to the ratio, is directly proportional to the gyromagnetic square of gyromagnetic ratio and the amplitude of the radio frequency pulse. I hope you are all with me and you can understand. Oh, so yeah. So if anyone has any doubt, you can ask.
Is the population difference just based on the magnetic field or some other elements are also responsible?
Population difference will depend on the magnetic field, because if you see this expression e to the power minus delta E by kT, then the delta is directly proportional to the magnetic field that is applied. So for delta what the expression in this expression, you can see that it is gamma h b naught by 2 pi. So the more the so you can so the more the external magnetic field, the more higher the B naught, the higher will be this ratio n beta by n alpha, and there will be a higher the population difference between the two energy states. So other than this, it
Got it.
also depends on the temperature. So how does it depend on the temperature? So the lower the temperature, this e to the power, actually here there is a mistake. N beta by n alpha will be equal to e to the power plus delta E by kT. So what will happen? The lower the temperature, this delta E by kT will be more, and hence the ratio will increase. Usually what happens, so nowadays what we are sometimes people use cryoprobes. The this is because of the to increase the population difference between the two states. So the lower the temperature, there will be more difference between the two state, and hence the sensitivity of detecting the signal increases. I hope that is clear. Or
Yes, thank you.
Excellent explanation.
now what happens is the what is resonance conduction condition. We learned about what is the nuclear magnetic moment. Now coming to the resonance condition. The now what we learned is that the nucleus is processing about the magnetic field with a particular frequency, which is given by omega naught. Now, if a same frequency, if a radio frequency having the same frequency as that of the precision frequency, or as that of the uh, is equal to the frequency with which the nucleus is processing about the magnetic field is applied, then that is called the resonance condition. So in what will happen in the resonance condition, the nuclei which are present in the lower energy level, they will move to the higher energy level, and there will be transitions of the nuclear spins, and this is given by the expression nu equal to gamma h naught by 2 pi. So, and one more thing that we have to keep in mind is the sensitivity of the NMR signal detection depends on both the gyromagnetic ratio and the natural abundance of the isotope. So there are different NMR active nuclei, for example, there is proton 1, H1, there is N15, and so any nuclei that we have, any element in the periodic table, they all have isotopes. For example, if that is hydrogen, it has a isotope which is deuterium. Proton has isotope deuterium. Similarly, if there is carbon 12, then its isotope is C13. So the abundance of the isotope, what is the abundance of the isotope, that also will determine the sensitivity of the NMR signal detection. Now, now the nuclei are processing about the magnetic field, and it also has a magnetic moment. Now, the magnetic moment, we can resolve the magnetic moment into components in the z-axis and the x-axis and y-axis. So all the nuclear magnetic moment along the z-axis of the nuclear spin gets added up, and what is bulk magnetization? Basically, what happens is that the magnetic moment along the z-axis, the vector sum of the magnetic moments along the z-axis is so there are nuclei which are processing in the alpha state, and there are nuclei which are processing in the beta state. Now, the nuclei which are processing in the alpha state, the if we take the magnetic moment along the z-axis, and the vector sum of that magnetic moment uh, becomes greater than the vector sum of the magnetic moments which are in the beta state. Why does this happen? Because as we already discussed, that in the alpha state, the number of nuclei are more, population of nuclei in the alpha state are more than that in the beta state. So this gives a resultant magnetization in the positive z-axis, and the vector sum of this magnetic moment along the z-axis is called the bulk magnetization. And here another concept comes, which is known as random phase approximation. So the magnetic moment will have a component in the z direction, and also it will have components in the x and y direction. Now, in the x and y direction, what happens that since these nuclei are are randomly oriented along about the z-axis. So a component of the magnetic moment along the x-axis get cancelled by an equal and opposite magnetic moment in the negative x-axis, and in this way all the magnetic moments in the x and y-axis get cancelled, and since they are randomly oriented, we consider that in the xy plane the magnetization is considered to be zero. So, what is random phase approximation? It is the sum of magnetic moments in the xy planes cancel out each other as they have equal probability of being in any direction of the xy plane. In the equilibrium condition, the bulk magnetization remains along the z-axis, and the magnetization and in the x and y axis or in the transverse planes are considered to be zero by this principle of random phase approximation. Now, when radio frequency pulse is applied in a direction perpendicular to the bulk magnetization, the bulk magnetization shifts from the z-axis to depending on the direction of the radio frequency pulse, it will shift. If, for example, if the pulse is applied in the x-axis, then the bulk magnetization shifts from the z-axis to the y-axis, and now the nuclei will start precessing about the y-axis in the xy plane. So here one more concept comes into play is the rotating frame concept. So what happens in the rotating frame? If a frequency is applied, um, if a frequency is applied which is equal, so for example, we are applying a radio frequency pulse which is having a frequency omega 1, and this omega 1 is equal to the frequency of the rotation of the nuclei, then it will be equal to gamma h1. In this case, the bulk magnetization will move to the since this radio frequency pulse is applied in a direction perpendicular to the bulk magnetization, it will move to the y-axis or the x-axis depending on the direction of RF pulse. And if the radio frequency pulse has a frequency which is different from that of the um, frequency of the with which the nucleus is precessing, then we have to take the resultant magnetic field, which will be root over h1 square by h naught square. So I hope this is clear. So in rotating frame, what is basically happening is that we are providing a radio frequency pulse which is having the same frequency as that of the frequency with which the nucleus is precessing. And so what happens? The external magnetic field B naught we can consider that it becomes zero, because since the radio frequency pulse frequency matches the frequency of this frequency with which the nuclei are precessing, the now what will happen, the nuclei will start precessing about the magnetic field of the radio frequency pulse, which is h1. H1 is the magnetic field of the radio frequency pulse, and h naught is the magnetic externally applied magnetic field. So, what is the advantage of this rotating frame? Why do we need to move into this rotating frame? So here, the advantage is that the externally applied magnetic field has a very high value. It is in range of megahertz. Now, now in the megahertz, the calculation becomes difficult, and so if we want in the rotating frame, this h naught becomes zero, and so in this case, the h naught becomes zero, and the h1, the radio frequency, has a magnetic field in the range of kilohertz. So the so the Um, uh, the calculations become easy, and now we can consider that the external magnetic field has disappeared, and the nuclei is only precessing about the magnetic field of the radio frequency pulse. And now there was another concept introduced, which was the relaxation. So what is the T? So they have two relaxation, T2 relaxation and T1 relaxation. And so what happens when this radio? So what when the energy is provided in the form of short pulses, short bursts of energy, which is known as the radio frequency pulse. And once this radio frequency pulse is removed, the nuclear spin, the nuclear spin which had started. Which had oriented in the x direction, which had shifted from the z direction to the x direction, and the nuclei was precessing around the first. So first the nucleus was precessing around the z axis. Now, when a radio frequency pulse is applied, the bulk magnetization shifts from the z axis to the y-axis, and the nuclei starts precessing about the y-axis. Now, when this radio frequency pulse is removed, the bulk magnetization starts to move to its equilibrium position, and the time that the nuclear spin takes to move from this xy plane back to the z axis, that is given by T2 relaxation, or it is also known as spin relaxation or transverse relaxation. Now, now, along with the nuclear spins, so here there are two things. One is the nuclear spins which were rotating around the x-axis, and another is the bulk magnetization, which had now shifted to the y-axis. So when the radio frequency is removed, the bulk magnetization, which had oriented along the y-axis, that shifts. That will, in absence of the radio frequency pulse, that will shift back to the z-axis, to the z-axis, and the time that is required for the growth of signal along the z-axis is called the T1 relaxation, or it is called the spin relaxation and longitudinal relaxation. So for example, this is the z-axis. Sorry. Uh, so and this is the externally applied magnetic field B naught, or you can also call it H naught. So I hope you have gone through this figure. It is there in the lecture. So now if the
Continue,
now
continue.
yeah, so what happens is so our externally applied magnetic field is oriented along the z-axis. Now what we are doing, we are applying a radio frequency pulse along the, for example, we are applying it along the x-axis. Now this radio frequency pulse causes the this bulk magnetization to shift from the z-axis to the y-axis. Now what will happen? The bulk magnetization is will shift to the y-axis, and the nuclei will now start precessing about the y-axis. Now, when this radio frequency pulse is removed, the bulk magnetization, which had shifted from the y-axis, will again start to move from the y-axis to the z-axis, or then it will. So there will be two things that will be happening. One is this bulk magnetization will move from this xy plane to the z-axis, and that is that the time that is required is called the T1 relaxation, and also the nuclei which were precessing in the XY in this XZ plane, they will start dephasing out and from the XY plane, and they will move into they will again move back to the equilibrium position and start rotating around the Z axis. So the bulb and that is given by this T1 and T2. These things. So yeah, yeah. I hope that is clear. And so this is a table which summarizes the NMR, the different isotopes, what are their natural abundance, and the gyromagnetic ratio of these different nuclei, proton, deuterium, B11, C13. From this table, what you can see is that this proton has the highest gyromagnetic ratio, and its natural abundance is also highest. And then followed by this, we have P31. P31 has a very high natural abundance, 100%, and the gyromagnetic ratio is also high. What I had said in that in the previous slides, that the sensitivity of of detection of the NMR signal depends on both this natural abundance and gyromagnetic ratio. For few nuclei like H1 and C13, which are commonly used in biology, which are very common in biological macromolecules, it is you can remember the gyromagnetic ratio. This gamma is in units of radian per Tesla per second, and it is 26.753 into 10 to the power 7. All these are have a multiplication factor of 10 to the power 7. One thing to note over here is that this H1 and C13, the gyromagnetic ratio. Yeah, so the gyromagnetic ratio of C13 is 1/4 that of the proton of the H1 nucleus. So I hope all the points were clear, uh, and if you have any doubts, you can ask, or you can also share whatever you know about this, whatever you have understood about these concepts. So now, so that was the summary of week one lecture, and now let's solve a few questions so that you can understand all the concepts better, and this will also help you in solving your assignment. So the first question is the so what we will do is I'll give 5 minutes for you to think about the question, and then after 5 minutes, you can post your answer, and then we can discuss the question. So the first question is, the radio frequency falls in which range of the following? Um, so there are four options: 10 to the power 6 to 10 to the power 10, 10 to the power 10 to 10 to the power 12, 10 to the power 12 to 10 to the power 13, and 10 to the power 13 to 10 to the power 14. So So if anyone knows the answer, you can post it in chat, or you can also unmute and answer the question.
Option 1.
Yeah. Option 1, any other answer? So we will wait for another 2 to 3 minutes.
1.
Yeah. So this is a very easy question, and if you have ever been in an NMR lab, you must have seen that the radio frequency, the NMR instruments, um they have everything in written in megahertz, 200 megahertz, 300 megahertz. So megahertz stands for 10 to the power minus 6, 10 to the power, sorry, 10 to the power 6. Yeah, this is the answer. The answer, yeah, Arpita, you answered it correct. The answer is option one, and here there is a table which shows the frequency of different electromagnetic radiations. The radio frequency has the shortest energy, and so its frequency is also the shortest among all the different electromagnetic radiations. It lies between 10 to the power 10 to the power 6 to 10 to the power 10, and the that is the answer, 10 to the power 6 to 10 to the power 10. Now, moving to the next question. So, this is the second question, which asks you about the correct option, which has all the nuclei that have non-zero magnetic moment. So, what who can so what no, who can answer this? You can try this, and then we can discuss after 5 minutes. So which nuclei will have non-zero magnetic moment? Anyone? Anyone?
Four.
Yeah, okay. Okay, any more answers? Yeah, so any nuclei which have spin quantum number I equal to 0 will have a magnetic moment mu equal to 0, because we had seen in the summary slides that the nuclear magnetic moment mu is directly proportional to the uh, spin angular momentum, and spin angular momentum is related to the spin quantum number I. So if the spin quantum number I equal to 0 is equal to 0, then the angular spin angular momentum will be 0, and hence the nuclear magnetic moment will be 0. Uh, so uh, now that was the hint, and then you can think about which will be the correct option. So there is an empirical rule that we follow for determining whether a nuclei is NMR active or NMR inactive. We see the mass number and the atomic number. Um, so So if we see the first option, H1, it has an atomic number 1 and mass number is 1. So uh, yeah, Guddu, your answer was correct. The answer is option 4. So what is the so how do we decide whether the spin quantum number will be 0 or non-zero? So if both the atomic number and mass number are even, then I will be equal to 0. If the atomic number is odd and mass number is even, then I will be equal to 1, 2, 3, and will be in the numbers will be in 1, 2, 3. And if the atomic number and mass number both are even, sorry, if both are odd, this will be odd. I have written this wrong. I'll correct this. If both atomic number and mass number are odd, then the spin quantum number will be in integers of half, in multiples of half, 3 by 2, 5 by 2. So if we see the first option, the H1 proton, it has both atomic number and mass number 1. So I will be half. For O17, it has a mass number of yeah, it has a odd mass number and an even atomic number. So it will also have spin quantum number and N15 has a mass number 15 and atomic number is 17. And atomic number is 7. So both the mass number and atomic number are odd. So it will also have a value of I. For S32, S32 has both the atomic number and mass number even. Its atomic number is 16 and mass number is 32. So in this case, for S32, the spin quantum number is 0, and it will have a 0 magnetic moment. Similarly, we can see for the other options in option 2, F19, C13, and H2. These three nuclei are NMR active, while O16 is NMR inactive. In the third option, N14, C12, sorry, N14, H1. These two are NMR active, while C12 is NMR inactive. This B10 is also NMR active because it has an atomic number of 5, and so its atomic number is odd, so it will have a value of I. And in the fourth option, all the nuclei have a spin quantum number, and hence they will have a non-zero magnetic moment. So I hope this question was clear. So you can correct this one. I have written this by mistake. This will be if both atomic number and mass number are odd. So moving to the third question. So the third questions ask about the number of orientations that is possible for a nuclei with spin quantum number I equal to 3 by 2. So if anyone has solved, you can give the answer.
Second number.
Yeah. Okay. We will wait for others and then we can discuss the question. So as we discussed, the number of orientations that is possible for a nuclei with spin I is equal to minus I to plus I. So if the spin is I equal to 3 by 2, then the number of possible orientations will be minus 3 by 2 to plus 3 by 2 with increments of plus 1. And so there is a direct formula for finding the number of orientations, which we also discussed in the summary slides, that it is 2i plus 1. So you can apply the formula 2i plus 1 and then tell me the answer. So here I is 3 by 2. So putting the value of I equal to 3 by 2, we will get 2 into, yeah, yes, the answer is option 2. The number of orientations will be 4. So if we put the value of 3 by 2 in this equation, in this formula 2i plus 1, we get the number of orientations as 4. So what is the meaning of this? The nuclei will have these many orientation. It means that when we are applying in presence of the magnetic field, the energy level will split into 4 different energy levels with uh, so the degeneracy gets lost in presence of the magnetic field, and it splits into 4 different energy levels, which will be minus 3 by 2. Then what? Minus half, plus half, and 3 by 2. I hope that is clear. Now moving to the next question. So this is similar to the question that we solved in the previous question. So in the previous question, we were asked to find out the number of orientation. So we have to find the magnetic quantum numbers of a nuclei which has a spin I equal to 3 by 2. So all of you calculate and let me know. So the magnetic quantum numbers will be minus I to plus I, and they will minus I to plus I with increments of plus 1. So if the spin quantum number is 3 by 2, then its magnetic quantum number will be between minus 3 by 2 and plus 3 by 2. So as we discussed, that it will have 4 different quantum numbers, and the 4 different quantum numbers will be minus 3 by 2, minus half, plus half, and 3 by 2. So the correct answer is option 4. So I hope this concept is clear.
Yes, clear.
Okay. So moving to the next question, question number 5. So in question number 5, is the question 5 asks to find the frequency of a proton which is present in a magnetic field of 17.1 Tesla. So what will be the frequency of a proton in a magnetic field of 17.1 Tesla?
Second option,
Yeah.
750 megahertz.
Okay. So how did you find it out? I think you are not audible. You have kept yourself mute.
It's a formula to multiply with the 17.1. This one is the
Hmm.
magnetic field, okay? And
Okay.
the 42.57 और जो मेगा हर्ट्स अपना उससे मल्टीप्लाई करके और जो मैग्नेटिक फील्ड का रेशियो है देन गॉट द 750 मेगा हर्ट्स.
Okay. Yeah. Yeah, it's correct. Yeah. So so as Guddu said, yes, it is the answer is 750 megahertz. We know this the frequency of a proton in a magnetic field will be nu equal to gamma b naught. Okay, so the gamma is the gyromagnetic ratio, and this gyromagnetic ratio we said that the gyromagnetic ratio of proton is 26.753 into 10 to the power 7 radian per Tesla per second. But in units of megahertz per Tesla, the gyromagnetic ratio is equal to 42.577 megahertz per Tesla. So it is better if you can remember this, that one Tesla is equal to 42.577 megahertz. There are a few questions in our assignment of this type. Since the gyromagnetic ratio is 42.577 megahertz per Tesla, and the proton is present in a magnetic field of 17.1 Tesla, we will multiply this gyromagnetic ratio with this magnetic field, and we will get this gives an approximate value of 750 megahertz. So this is the frequency. This frequency is also known as the Larmor frequency, and this is the frequency with which a uh, nuclei precesses, or it is rotating with this frequency around the externally applied magnetic field. And this is given by this expression nu equal to gamma b naught. So you can find the Larmor frequency for not only for proton but also for other nuclei C13 or N15. So if you know the gyromagnetic ratio of the nuclei, then multiplying it with this magnetic field will give you the Larmor precision, or the Larmor frequency, or we can say that frequency with which this nuclei is rotating about the externally applied magnetic field. Now, one thing to note over here is that the gyromagnetic ratio is 42.577 megahertz Tesla. This is true for proton for each one nuclei. For other nuclei, I had already shown a slide. Um, Previous slide, there was a table. This has the gyromagnetic ratio of different nuclei. So accordingly, you can calculate the frequency of the nuclei in a particular magnetic field. So we will move to the next question. So here you have to determine the order of sensitivity of nuclei. There are four options. So there are mainly four nuclei: proton, P31, C39, and N15. So you have to arrange the order of sensitivity of the nuclei. For these four nuclei, you have to arrange what is the you have to say determine what is the correct order for these four nuclei with respect to sensitivity. So. Take your time and then we will discuss the answer in 5 minutes. So has anyone tried this? So I can give you a hint. So you can see the values of this of gyromagnetic ratio, natural abundance of different nuclei in this table, and then you can, as you know, that the sensitivity is depends on the natural abundance of the nuclei and also its gyromagnetic ratio. So any nuclei that has a higher natural abundance and gyromagnetic ratio will have a higher sensitivity of NMR signal. So you can look at this table and then you can decide.
One.
Yeah. Yeah. So in this table, what you see is that this proton has both natural has higher natural abundance and gyromagnetic ratio, followed by this P31. His natural abundance is 100%, and then the other nuclei that was there was C13. C13 C13 also has so its sensitivity will be lesser than this proton and nitrogen 15, and then followed by nitrogen 50. Nitrogen 50 will have the least sensitivity because it has a negative gyromagnetic ratio. So yeah, the answer is option one. Yeah. Option one. So yeah, the sensitivity is proportional to the gyromagnetic ratio and natural abundance. So a nuclei which is having both higher natural abundance and gyromagnetic ratio will have a higher sensitivity.
Meaning of here the higher sensitivity means the we saw the mm, peak of these isotopes will
So
higher.
so what is meant by higher sensitivity? It means that the energy difference between the alpha state and the beta state will be higher, and so the detection of the NMR signal in case of nuclei which has higher sensitivity will be better than a nuclei which has lower sensitivity. So usually in most cases this proton H1 NMR is done because this has a very higher this has a high sensitivity, and so the detection of the NMR signal becomes easier. While the other nuclei are also when we are performing an NMR experiment, we also use the other nuclei, but the most frequently used is proton NMR because it has a higher sensitivity and the detection of signal is better in case of H1. While for other, we have to use other techniques, and these we will learn in subsequent weeks. So basically, higher sensitivity means that the detection of the NMR signal becomes better if a nuclei has higher sensitivity.
Thank you.
And the energy difference for nuclei which has higher sensitivity will be more. The delta E gamma HB naught by 2 pi, that the energy difference is higher for a nuclei which has higher sensitivity compared to a nuclei which has lower sensitivity. So since the energy difference is directly proportional to gamma, so a nucleus which has a higher gyromagnetic ratio will have a higher energy difference, and hence its sensitivity will of detection of the NMR signal will also be more. And one more way we can increase the sensitivity is by increasing the magnetic field. So if a nuclei has poor sensitivity, then we need to use a NMR instrument which has a higher uses a higher magnetic field, or its frequency. The frequency of the NMR instrument is more, so we need to go to higher frequency of spectrometers, 750 megahertz, 800, 950, and we can go up till 1.2 gigahertz. So there are there are other methods also, but the main factor which controls the sensitivity are these gyromagnetic ratio and natural abundance. Now moving to this next question. So the next question is, if a proton absorbs at a frequency of 750 megahertz, then carbon 13, so this is carbon 13, will absorb at a frequency of approximately. So for this question, you need the gyromagnetic ratio of proton and gyromagnetic ratio of carbon. So the gyromagnetic ratio I have not written in this question, but it is better if you can remember their gyromagnetic value of their gyromagnetic ratio. So for a proton, it is 26.753 into 10 to the power 7 radian per Tesla per second. And for carbon, it is 6.728 into 10 to the power 7. So the value is written in this slide. So you can note down the value of the gyromagnetic ratio of this proton and carbon 13 from this table. So all this gyromagnetic ratio has a multiplication factor 10 to the power 7. So I think you have noted, I hope you have noted down the values of the gyromagnetic ratio. And now you can solve this question. You can try out this question. So any nuclei will absorb at a frequency which is given by, we saw it in the previous slide also, it is omega naught equal to gamma B naught. So everyone try this question and tell me the answer, and then we can discuss it.
Option 1, 188 megahertz.
Okay. Any other answer? So Guddu, can you explain how you solve this question?
Yeah, here I take the firstly the ratio, gyromagnetic ratio of the proton and carbon,
Okay.
and then frequency, find the frequency, then we get the first proton frequency is the 750 megahertz, and
Okay.
then we calculate according to the equation ki F1 frequency is equal to the proton and then divided by its assumption carbon frequency is X,
Okay. Yeah,
and
correct.
solve the equation after dividing the proton gyromagnetic ratio and carbon gyromagnetic ratio. We find the value X is equal to 188 megahertz.
Yeah, it's correct. Good. It's correct. Absolutely correct. So yeah, basically you have to find the ratio of the gyromagnet. You have to. You can. So what Guddu explained is you have to find the ratio of the values of the gyromagnetic ratio of the two nuclei, carbon 13 and proton, and one good thing to remember is that the carbon 13 has almost one-fourth the value of gyromagnetic ratio of proton. So the gyromagnetic ratio of carbon is approximately one-fourth the gyromagnetic ratio of proton. So accordingly, you can solve and find the answer. So yeah, so when a magnet this magnetic moment interacts with the external magnetic field, the energy of interaction is given by this formula equal to minus mu z into h naught, and the magnetic moment along the z axis, this is mh gamma h naught by 2 pi, or you can directly use the formula E equal to gamma into b naught. That is also correct because this m value of the magnetic quantum number of both carbon 13 and proton is half. So basically you have to you can get the value of the frequency that with which carbon will absorb by finding the ratio of the two, by taking the ratio of energy of proton and energy of carbon, and this will be equal to the ratio of gyromagnetic the ratio of gamma value for proton and gamma value for carbon, and since both these nuclei are placed in the same magnetic field, we are using the same NMR instrument for recording this. So the H naught, the externally applied magnetic field, is same for both the cases, and hence the H naught gets cancelled when we take the ratio. And so what we are left with is 750 by X equal to 26.753 into 10 to the power 7 divided by 6.728 into 10 to the power 7, which gives an approximate value of 180 megahertz. So this energy you can express in units of megahertz, or you can because energy is will be proportional to the frequency, so you directly use omega equal to gamma into b naught. That will also be correct, omega equal to gamma into b naught. So the frequency with which any nuclei absorbs radio frequency will be gamma b naught. So directly, if you use that formula, then also you can solve this question. Yeah. So moving to the next question, the number of degenerate states of a nuclei with spin of 2 will be 3, 6, 2, 5. So solve this question and let me know the answer. So anyone solved this? Could anyone solve this question? So what is the answer? So in presence of the magnetic field, the degeneracy of the nuclei is lost. So what is the degeneracy? The all the nuclei will be in the same energy state. But when they are placed in an external magnetic field, the the energy levels separate, they become degenerate, and the nuclei will get distributed in different energy levels. So so both the we also discussed a question in the second or third question. It was also similar to this one. So whether it is asked to find the number of orientations of the nuclei in a magnetic field, or you have been asked to find the number of degenerate state, the formula is the same. You have to use 2i plus 1. So the number of degenerate states will be 2i plus 1, and here what is I? I here is here I is given as 2. So using the formula, you can calculate the number of degenerate states. So they are present in a particular energy. They are present in a particular. All the nuclei have the same energy in absence of magnetic field. And now when magnetic field is applied, they will become degenerate, which means that they will have different energies. So for spin equal to 2, if I is equal to 2, so in this question, what is I? I is 2. So it is 2. And so how many energy levels it will have? How many degenerate states it will have? So it will be 2i plus 1, which will be 5. And what will be the magnetic quantum number of these energy states? Who can tell? So it will be, the correct answer is option 4. 2 into 2 plus 1, 5. So it will be minus 2. 1 will be minus 2. Then minus 1. Then 0. 1 and 2. So here the magnetic moment will be m equal to minus 2. Sorry, the magnetic quantum number minus 2. These are the, or if you want to, yeah. So in terms of energy, if the magnetic quantum number is minus 2, then it will have it has a higher energy. So the magnetic quantum number m equal to minus 2 will have a higher energy. This will be m equal to minus 1. This is 0 for magnetic quantum number. 0, this will be the energy level. Then 1 and 2. So these are the different energy levels in presence of the magnetic field. The degeneracy will be the nuclei will become degenerate, and they will be oriented in these energy levels. The nuclei will get oriented in these energy levels.
Okay, my question is if we increase the number of a speed, okay, then the degenerative state will increase also.
Yeah, it will increase. The number of degenerate states will increase if it has a higher spin quantum number.
Okay, then what is the relevance between the spin and degenerative state? If the degenerative state and a spin both are increased, then what the significance to the my experiment when we perform?
So regarding the significance, these concepts will be discussed in the subsequent weeks. So what will happen is now when the number of energy levels increases, the nuclei will all the nuclei will get distributed in this uh, five different energy levels, and we will learn about how these their interaction with radio frequency, and what will be the effect of such nuclei when they are used for NMR experiments in the later weeks. So we can discuss them in the subsequent weeks. So yeah,
Thank
this is
you.
the solution. Hmm. Okay. So moving to the next question. So in question number 9, the question asked here is a radio frequency pulse 2H1 cos omega t is applied to a protein sample. The RF induced transition probability between the energy levels is given by. So, radio frequency pulse is an electromagnetic radiation, and since it is a wave, we can express it in in this equation in the form of this equation 2h1 cos omega. This is a wave function 2h1 cos omega t, and when this radio frequency is pulse is applied, what will be the transition probability between the transition probability of the nuclear spin to move from alpha state to beta state or vice versa. So what will be the answer of this question? So what is transition probability? So in presence of magnetic field, so this is my alpha state. So we can say this is the alpha state and this is the beta state. So the beta state will have a magnetic quantum number m equal to, so alpha state has a magnetic quantum number half, and this will have a quantum number minus half. And so these are the nuclei, and so there will be. So actually, this is the quantum mechanical picture. But if in the classical mechanics picture, we can see that this alpha state has a lower energy, and this beta state will have a higher energy, and there will be more number of nuclei which are present in the alpha state. So if there are these are the nuclei. So for example, there are 3 nuclei, and there will be, for example, there are 2 nuclei. So is this one. So what is the transition for what? So what is the probability for transition of a nuclei from this alpha state to beta state? So the transition probability P is given by, it is directly proportional to gamma square H square. Gamma square H square, and so we remove the proportionality, then it is 1 by 4 gamma square H square. So this expression we get from from the Boltzmann statistics, the expression that I had shown, n beta by n alpha equal to e to the power minus del E by kBt. So from that equation and from a few quantum mechanics concept, you can solve this and you can find the transition probability, and the expression is given by this equation that the transition probability P is equal to 1 by 4 gamma square H square. So what will be the answer for this question? So it will be equal to the square of the amplitude of the radio frequency pulse H1 and the gyromagnetic ratio of the nuclei. So it will be equal to proportional to H1 square gamma square. So the answer will be option 4, isn't it? Yeah. So is this? Now I hope this question was clear, and you can remember this formula that the transition probability is always proportional to this gamma square and H1 square. And moving to the next question. So why is NMR spectroscopy considered a very insensitive technique? So there are four options given: small population difference between the alpha and beta spin states, the interaction of matter with radio frequency, the saturation of nuclear spins in the energy levels when the radio frequency pulse is applied, and the fourth option is all of the above. So, so if you have gone through the lectures, then this is a pretty easy question. So this question does not require any numerical to solve any numerical. So if anyone knows the answer, can unmute yourself and say the answer. So basically, it is a very insensitive technique because there is a what is the answer would do?
One option. A
Yeah,
small
option.
difference between the
Yeah.
alpha and beta spin states.
Yeah, and why is it so?
And now previously question you discussed the Boltzmann the expression
Mm-hmm.
why the
Yeah.
alpha and the beta state takes a role in the sensitivity and the
Mm.
energy state difference between them.
Mm. Yeah. Yeah, absolutely correct. So the answer is there is a very small population difference between the alpha and beta spin states. The alpha spin state has a relatively higher number of nuclei compared to the beta spin states because the in the alpha state, the energy of alpha state is lower and the energy of beta state is higher. So the alpha state has a lower energy, and hence there is more number of nuclei in the alpha state compared to the beta state. But the difference in the number of nuclei between the alpha state and beta state is extremely small, and so it is a very insensitive technique. So if we want to increase the difference between the alpha state and beta state, what we have to do? So for example, this is the alpha state and this is the beta state. So this is the beta state. So if we increase the, sorry, actually. This is the beta state. If we want to increase the population difference between these two energy state, then what we have to do? So we have to increase the energy difference between these two states, delta E. What is delta E? Delta E is the, so if we increase the energy difference between the alpha state and beta state, what will happen? So for example, this is the alpha state and beta state in one case, and this is the alpha state and beta state for another nuclei, for example, or we are recording the NMR signals in a different NMR instrument which has a higher frequency. Then in that case, the delta E, the separation, if we see, the separation between these two energy levels has increased. So the more the separation between these two energy levels, the more there will be fewer number of nuclei in the beta state, and hence what will happen? The population difference will increase. So what we have to do to increase the population difference? So we have to increase the energy difference between these two states. So if we can increase the energy difference between these two states, then the population difference between the alpha and beta spin states will also increase. Okay, and so the correct answer in this for this question is small population difference between the alpha and the beta spin state. And second option, interaction of matter with radio frequency. This is wrong. The saturation of nuclear spins and energy level when RF pulse is applied. This is also wrong. What is meant by the saturation of nuclear spins? Who can say saturation of nuclear spin? And when does this happen? So saturation of your nuclear spin means that if the number of nuclei in the alpha state and the number of nuclei in the beta state becomes exactly equal. If they become equal, then that is called the saturation state. Okay, and when will this happen? When will saturation of nuclear spins happen? When does saturation of nuclear spin happens? So if you are, for example, if you are continuously applying a radio frequency pulse, then then an equilibrium state will be attained where the number of spins in the alpha state will become equal to the beta state. And in that case, what will happen if there is saturation of nuclear spin? We will not get any NMR signal, because the NMR signal, we are getting the NMR signal because of the difference in the number of nuclei in these two states. But if the number of nuclei become equal, then there will be no NMR signal. Hope that is clear. Yeah. So by Boltzmann statistics, n beta by n alpha equal to e to the power minus delta E by kt. So NMR is an insensitive technique due to the very small population difference between the alpha and the beta states. And also we know that the alpha state has more number of spins than the beta state. Is the correct answer. Moving to the next question. In this question, you have to find the Larmor precision frequency of C13 in a magnetic field. What is given in this question? In this question, uh, the Larmor precision frequency of C13 nuclei in a magnetic field of 9.4 Tesla is given. It is 100 megahertz, and now we have increased the magnetic field to 18.8 Tesla. So if the magnetic field is increased, you have to find the Larmor precision frequency of proton. So all of you know the expression of Larmor precision frequency, nu equal to gamma b naught, or omega equal to gamma into b naught. So if you write it in expressions of omega naught, then it will be gamma b naught by 2 pi, But if you express it in terms of frequency nu, then it is nu equal to gamma into B naught. So you know the gamma for carbon 13 and gamma for proton, and also the magnetic field magnetic field is given in the question for what magnetic field we have used for C30 nuclei and what magnetic field has been used for this this proton. And now you can using this formula you can calculate the precision frequency. So solve this and let me know the answer.
Second option, 400 megahertz.
Okay. Anyone else? So how did you get 400 megahertz?
This one is the firstly we
Yeah. First, yeah, you use this formula, right?
yeah, and
And
then
you have taken the ratio of Larmor precision frequency of carbon 13 to
and
proton.
proton. Yeah.
Right, that is what you have done.
Then frequency dividing.
Yeah. Yeah. So you have divided the frequency of carbon 13 and
And proton.
proton. Okay. And then
Then we solve the equation after putting the value x, the find out the proton frequency, putting the value x, and the we know that the volume of carbon is frequency is 100, and then the
yeah, correct, correct. Okay, correct. And you can also solve this directly. Also, you can solve. So you know that the carbon 13 has a gamma 1/4 that of proton. So directly you can solve. So this is the solution of this question. The answer is correct. Yeah, good to you answered it correct. The answer is 400 megahertz. So basically, we have divided the Larmor precision frequency of proton to the precision frequency of carbon, and this will be equal to the gamma proton for the gamma proton by gamma carbon, and here I have not written one thing, so it will be into 100. So for proton you have to find yeah. So the you can. So you know the frequency for Larmor frequency for proton. You have to find the Larmor frequency of proton, and you know the Larmor frequency of carbon 13. It is 100 megahertz. So you put it in this equation, and then you can calculate you can find the value of x from this equation. So is this answer correct? Here in this question there is a mistake. Can anyone point out? There is a mistake in this question. The answer is not 400 megahertz. So you also have to consider the magnetic field, the ratio of magnetic field. So the ratio of magnetic field will be, so for proton, the magnetic field is how much? It is 18.8 Tesla. So I have made a mistake here. So it will be 18.8 Tesla. So can anyone solve this and let me know the answer? The answer is not 400 megahertz. Uh, Oh, it's actually becoming difficult to use the pen. So you have to multiply it by 18.8. So for the the magnetic field in which the proton is in which the NMR spectra of this proton is being recorded is 18.8 Tesla, and the magnetic field that we are using for carbon 13 is 100 megahertz. Is how much is 9.4 Tesla. So you have to multiply it by 18.8 divided by 9.4. So that will be how much? Yeah, 18.8 divided by 9.4 will be 2. And then yeah, so the correct answer will not, the correct answer is not 400, the correct answer will be 800. So here it is wrong. The correct answer is 800 megahertz. I will correct this in the slide, but I hope you have understood this question. So you have to also multiply the magnetic field in which this carbon 13 is present, and the magnetic field in which this proton is present. So you have to multiply it by 18.8 by 9.4. So 18.8 by 9.4, you will get 2. And so 400 into 2, the correct answer will be 800 megahertz. Okay, is it clear, Guddu?
Yes, clear.
Yeah. So the answer is not 400, it is 800. I will correct this in the slide. So now moving to this next question, for spin I equal to 1, the direction of orientation of spin angular momentum with respect to the magnetic field will be, have to tell me the correct option. So basically for a spin I equal to 1, there will be how many states? -1, 0, and +1. Okay.
Yes.
And each of these, and the nuclei in each of these states will precess around the magnetic field. So 0 is here. So this is. So this will be for I equal to 1, and for this will be the sorry. Wait 1 second. So for m equal to -1, this is the m equal to -1 state, and this is the m equal to +1 state, right? So this type of question was solved in lecture number 2. So what you have to find in this question is the angle, this theta. What is the value of theta? So what is the angle that this nuclear magnetic moment is making with the magnetic field? So this angle with respect to the z-axis. With respect to the z-axis, what is the angle made by the precessing that is made by the rotating nuclei with this z-axis, or with the magnetic field which is directed along the z-axis. So so how will you find this? So if you have gone through lecture number 2, you can follow this equation. So if you can see in this figure on the right hand side that for spin I equal to 1, this it will have three states: I equal to 0, I equal to -1, and I equal to +1. So for I equal to +1, what will be the spin angular momentum? The spin angular momentum will be equal to h by 2 pi root over I into I plus 1. So the spin angular momentum is this one, this the value of this. So the nuclei which is present in the m equal to +1 state, the nuclear magnetic moment will be h by 2 pi root over I into I plus 1. And if I equal to 1, you can calculate the spin angular momentum. It will be root over 2 h by 2 pi. And the spin angular momentum along the z-axis. So what is basically cos theta? Why are we calculating P and PZ? So cos theta will be equal to base by hypotenuse, that is PZ by P. So once we know the value of PZ and the value of P, then putting these values, we can calculate the value of theta. So yeah, I had also in the summary slides, you can go back to the summary slides and see the formula for the spin angular momentum along the z-axis and the spin angular momentum, which is of the nuclei, which is at a spin +1 state and spin -1 state, and using this by using a simple you have to find the angle. So you use cos theta equal to PZ by P, and so cos theta will come out to be 1 by root 2, and so theta will be 45 degree. Similarly, you can find for other nuclei also. If the spin is I equal to half, I equal to 3 by 2, such questions have already been solved in the lectures. So moving to the next question, the magnetic field of a rotating nuclei in terms of frequency is 3 kilohertz in the rotating frame. If the amplitude of radio frequency is 2 kilohertz, what is the effective magnetic field in frequency units? So for this question, you can see here that the radio frequency, the amplitude of radio frequency is different from the frequency with which the nuclei is rotating. So what you have to do here, so you have to take the vector addition of the amplitude of the radio frequency and the and the frequency of the rotating nuclei. So everything here is expressed in kilohertz. So you have to take their vector addition. So what will be their vector addition? It will be 3 square root over 3 square plus 2 square. So that will be equal to how much? That will be equal to root 13. So in the rotating frame, what happens is if the radio frequency the frequency of the radio frequency pulse is not equal to the frequency with which the nuclei is rotating, then we take the vector addition of we calculate the effective magnetic field, B effective. So B effective is given by is given by the vector addition of B naught and B1 vector, right? So B naught plus B1. And then so the vector addition will be equal to root over 3 square plus 2 square. So the correct answer for this question is root over 13. So you calculate the effective magnetic field. So this is the solution. And this is the last question for today. So the spin lattice relaxation T1 of a particular proton is 3 seconds on a 100 megahertz spectrometer. Is value on a 300 megahertz under the same solution conditions, and omega naught tau c much greater than 1 will be. So question is not visible. I don't know why is it I'm not able to present this, but I'll share this window. So the correct answer for this question is option number 2, greater than 3 seconds. And so I hope you remember this graph which was discussed in the lecture. For omega naught tau c much greater than 1, what happens that the T1 relaxation at 100 megahertz. So what is asked in the question is the spin lattice relaxation of a particular proton is 3 seconds on a 100 megahertz. So for 100 megahertz, if the T1 relaxation is 3 seconds, then if you move to the 300, if we move to 300 megahertz frequency, then at a condition omega naught tau c much greater than 1, the spin lattice relaxation time T1 will be greater than 3 seconds. Right, because you can see over here that for 100 megahertz, if the T1 comes at this position, then if for a 300 megahertz spectrometer, the T1 relaxation time will come at a higher value, right? So if this value is, for example, 3 seconds, then in a 300 megahertz spectrometer, its value will be greater than 3 seconds. The correct answer is option 2. So that was all, and I hope I could clear some of your concepts and some of your doubts. So if there, so you can go through the lecture once again, and if there are any more doubts, we can take up it in the next class. So thank you, everyone.
Thank you.
Thank you.